Okay, so we'll do a quick recap of what we had done in the yesterday's class. Um, so we defined what is a colloid. We just mentioned that it's any particle which has at least one linear dimension in the size range between 1 nanometer to 1 micrometer. Then we went through several examples in which I illustrated the motivation to study colloids. Namely, we looked at liposomes, which are used as carriers, for transporting things in medicine and cosmetic industry. We looked at ceramic processing, inspiration from nature, where we looked at structural colors, and superhydrophobic surfaces. Plus, I ended up talking about colloids as model atom to understand the phase behavior in materials, and how do we use colloids as a model system to look at such things. Okay, that's what we have done so far. So what I'll do today is hopefully these three topics. Okay, I've defined what is a colloid. Okay, we are going to look at what is a colloidal dispersion to begin with. Then we'll briefly talk about classification of colloids, and also we look at what is meant by what is called as a stability of colloids or stability of colloidal dispersions. Okay, that's the plan for this lecture. A colloidal dispersion is essentially defined as if you have colloids in a suspending medium, right? Therefore, now you have two components. You have colloid and you have suspending medium. So in the picture here, so you have these red things. These are the colloidal particles, okay, and the blue thing is the suspending medium. Now we have, as I said, more than one phase now, okay, and these dispersions essentially consist of at least two phases. There could be more. I may be looking at particles plus some other thing plus a fluid. Okay, there could be more than two as well. Okay, and typically these particles, which are present in such medium, they are what are called as a dispersed phase. Okay, that is these red particles here. They are the dispersed phase, and the liquid medium or a fluid medium in which the particles exist, it is what is called as a continuous medium. Okay, and of course, whenever you say a colloidal dispersion, dispersion is a homogeneous mixture. What I mean by homogeneous mixture is that imagine that I have this container. I take out a small sample volume. Okay, I go here and I take a small sample volume and find out what is, like, say, the number of particles present in that volume. Okay, now I go to another region. I take out the same volume of fluid. Okay, if the number of particles that you have in these two regions are essentially similar. Okay, you can't say it will be exactly same, but if they are similar in number, then I can say it's a homogeneous mixture, right? That means there are no continuous medium rich regions and a dispersed phase rich medium. Okay, so therefore the particles are homogeneously dispersed throughout the medium. Okay, so therefore you can say that colloids are actually homogeneous if you look at them on a what is called as a macroscopic scale. Okay, when I say macroscopic scale, I could think about like, say, some small volume of of course the dispersion as a whole, that's macroscopic. And of course, if I take a few mLs of fluids or few microliters of fluids, it is homogeneous macroscopically. However, if I go to the microscopic scale, or if I go to the a length scale which is of the order of particles or smaller than that, then it's not actually homogeneous, right? Because you have a solid and a liquid, or two different phases that exist, right? Therefore, colloidal dispersion, it's a homogeneous mixture of at least two phases, a dispersed phase and a continuous phase. And of course, you can have cases where I may have more than two phases as well. Okay, so that's what is called as a colloidal dispersion. Now, depending upon so in the previous example, okay, I said that the dispersed phase is a particle, right? But the dispersed phase can be of any different type. Okay, so So therefore, you can have different types of disperse phases, and of course different types of continuous phases as well, right. So if I have a continuous phase of gas, okay, and you may have liquid as dispersed phase, okay. If you have a system like that, okay, then you would have heard of a term called aerosol. Have you heard of this term, right? So aerosols, essentially what will happen is, like say if you like say for example fog, right? Fog is, you have water droplets which are condensed, right? These are water droplets condensed which exist in ambient air, okay. That is actually a dispersion of a liquid in gas, right? So similarly, I could have a solid in gas, okay. This could be, the vehicular emissions, the particulate matter that are emitted by vehicles. So if you have solid particles in these emissions, okay, that dispersed in ambient air again is an example where the dispersed phase is solid and the continuous phase is a gas, right. So for example, smoke, dust, even pollen grain, right, the particles that are of plant origin when they are in air, that's an example of aerosol. Of course, you could have continuous phases as a liquid, and the dispersed phase could be either gas, liquid, or a solid, okay. Now in colloids course, mostly you're going to look at this system, right. In most of the course that I'm going to teach, okay, you're going to have a solid particles dispersed in a liquid. They're what are called as sol, okay. Example of sols are, ink. If you take muddy water, which is actually example of clay particles in water, okay, or if you look at paint, for example, right. So all these are examples of sols in which the dispersed phase is a solid and the continuous phase is a liquid. Of course, there's a lot of interest in looking at emulsions and foams, right. So emulsions are liquid in liquid dispersions, and foams are gas in solid dispersions. Again, there are several examples that are listed here. We will mostly not look at cases where your continuous phase is solid, okay. There are other people who look at such systems, for example, an example of a solid emulsion, okay, could be liquid and solid, okay. For example, butter is an example of that, okay. A concrete which is solid and solid dispersion, right. But of course, these things people in other fields worry about. In classic colloids course, we will mostly look at systems where your dispersed phase is either gas, liquid, or solid, okay, and the continuous phases is liquid, okay. That's what we're going to look at mostly. Now, so you will, when you read up literature on colloids, you will see that there are several people who use the term colloidal dispersions or colloidal suspensions. So I just want to make terminology clear. So whenever people mention the term dispersion, typically the term dispersion is used when the size of the dispersed phase is in the colloidal size range, that is 1 nanometer to 1 micrometer. So whenever somebody says a colloidal dispersion, okay, then the size range has to be in the colloidal size limit, okay. And whenever somebody mentions a suspension, typically the size of the particles are larger than a micrometer, okay. So if I want to compare dispersions and suspensions, I can say that because of the fact that the particles in the dispersion are smaller in size, they exhibit a better stability for sedimentation. That means the things in a dispersion are more likely not to settle, whereas the suspension, because the particles are larger than a micron, the gravity may come into picture. If you have a container which is filled with particles, as a function of time, in a suspension you may see things settling at the bottom. However, dispersions may exhibit a better stability against sedimentation, okay. And you should also know a little bit about true solutions or solutions, which it actually refers to a molecular mixture, okay. So you can think about you take water and put in a salt, right? Or you take water and add a little bit of sugar, right? So in which case what you get is a molecular solution. In this solution, so typically the size of the dissolved species, okay, it is comparable to the size of the dispersed phase itself, the continuous phase itself, right? That means if I take salt, put it in water, if I look at the salt molecules, right, or Na plus and Cl minus, the size of that is very much comparable to the size of water molecules that you have in the system, right? So whenever the size of the dispersed phase and the continuous phase is comparable, that's when you refer to it as what is called as a true solution. Okay, so is the distinction clear? Yeah, yeah. Mm-hmm. Yeah. No, no. So, see, let's go back here. So, the question is something like this. So, he's asking a question. Look, we mentioned that the dispersed phase has to be in the colloidal size range, right? He's asking a question as to what about the continuous phase? Does it also have to be in the colloidal size range, right? See, when you say the colloidal, when you say the continuous phase, right? So, when you talk about, like say this case where we had, let me just do something, okay? Okay, let's look at this example, right? I'm going to look at this example, okay, where you have a dispersion of a solid, liquid, sorry, gas, liquid, or solid in a liquid, right? Now, these are the dispersed species, right? This is a continuous phase, okay? Now, the fact that the continuous phase is liquid, if you take liquid, which will have some molecules, right? If I take water or any organic solvent or any fluid, right, it will have some molecules. Obviously, the size of those molecules would be less than a nanometer, right? Right. So whenever we talk about colloids, right? So what we are talking about is a size of the dispersed phase. Okay. So in this case, continuous phase is liquid. Automatically, the length scale or size of the molecules are definitely even less smaller than the colloidal length scale. Okay. Is that answer your question? Yeah. 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 We'll talk a little bit about that. Yeah. So his question is, do they exhibit Brownian motion? So we'll talk a little bit about that in the few lectures to come. Now we'll move on to something called as classification of colloids. There are different ways of classification. In fact, you can even think about this particular table also as a classification, right? This is a classification based on the type of the dispersed phase and the continuous phase, right? You can also think about along those lines. Okay, therefore, if you were to classify colloids based on the type of the dispersed phase and the continuous phase, I can classify them into several different classes like emulsions, foams, salts, aerosols, things like that, right? So the other ways of looking at classification is based on the nature of interaction between dispersed phase and the continuous phase. Okay. Again, we'll talk a little bit more about interactions in the coming lectures. For today, what we'll do is when I say interaction, the only thing that I mean is whether the dispersed phase and the continuous phase like each other or they don't like each other. Okay, it's a very loose term. Okay, so therefore, in colloids, what are called as lyophilic colloids. Okay, lyophilic colloids. Lyo means liquid. Philic means something that likes a liquid. Okay, so therefore, in such colloids, the dispersed phase likes the dispersion medium. Okay, the dispersed phase likes the dispersion medium. So in such colloids, the dispersed phase does not precipitate out easily. Okay, if you put such particles in water, it doesn't precipitate out or it doesn't settle down or it doesn't aggregate and form large clumps, okay, and the salts are quite stable, okay. An example is given something here. I'll tell you what exactly this vial is in a while. In what is called as lyophobic colloids, the dispersed phase has little affinity, okay. There may be some affinity towards the dispersion medium, or it may not like it, okay. And these colloids, they easily precipitate out of the solution, and therefore such dispersions are typically not stable, okay. So what you are looking at, the vial 1, what we had done is, we went to one of our colleagues' lab, we got CNT, right, carbon nanotube, which are commercially available. We took these particles, we put them in water, okay. We try to mix them, okay. As I said, typically for mixing, people use either sonication or high energy mixing or manual shaking, okay, depending upon the kind of system that you're working with, okay. So therefore these are pure CNT, okay, or CNT as received, right, in water, okay. No matter what you do, you mix them and leave it for a while, you can clearly see there's a phase separation, right. There's a liquid here, that's water, and then all the particles are at the bottom, okay. So this is an example of what are called as lyophobic colloids. I can also call them as hydrophobic, because in this case the dispersion medium is water, okay. They are example of hydrophobic colloids which do not disperse in water and they would like to phase separate, okay. Now in this vial, what was done is, we took exactly same particles as received, and then we did what is called as a surface functionalization, okay. Again, the details are not important. The surface functionalization is done as simple as taking these CNT particles, put them in an acid solution, okay, and then sonicate for some time. So the idea is, you have the CNT molecules, and on these molecules you can form some acid groups, okay, maybe CO minus or something like that, okay. Now we take such particles, put them in water, and then they happily disperse, okay. So therefore, whether a particle is a hydrophilic colloid or a hydrophobic colloid, or lyophilic colloid or a lyophobic colloid, it really doesn't depend on the type of the colloid that you are working with, okay. What it really matters is what is the surface functionalization, right. That's important, and we'll talk a little bit about that in the coming classes as well, okay. So therefore, in this kind of classification, based on the nature of interaction medium between the dispersed phase and the continuous phase, when I say the nature, what I mean is whether the particles likes the dispersion medium or does not like, depending upon that, you can classify them as lyophilic colloids and lyophobic colloids, okay. That's one. So we can also classify colloids based on the types of particles that are dispersed, okay. I had shown this triangular diagram in the last class. So you have polymers here. What is written here is a colloid, okay. Now what can you say about this particular picture? What can you say about this particular picture? Okay, so while you guys think, okay, the third apex is amphiphiles, right. What it actually tells you is that if you take any colloidal particle, okay, this colloidal particle is essentially made up of a lot of atoms, right, or the molecules. Whenever I say I have a gold particle, okay, of course it is made up of several gold atoms, okay, right. Therefore, so if you have such solid particles, okay, which are dispersed in a fluid, it is what is called as a multi-molecular colloids, because each particle is made up of a large number of atoms are the molecules, okay, which are essentially dispersions of solid particles in a liquid. Okay. Examples could be, as I said, right, if I have water with say gold particles, or the CNT that I talked about, or any kind of solid particles in a fluid, that's an example of what is called as a multi-molecular colloids. Second type of dispersed species that people work with, it is what is called as a macro molecular colloid, which essentially are dispersions of polymer in a solvent. Okay, so the polymer, another name for polymer is macromolecule, right? A large molecule which is essentially made up of large number of repeating units, right? That's what we talked about in yesterday's class. And the third type of colloids are what are called as association colloids. Any thoughts what association colloids could be? Okay, the name already tells you something, right? Okay, they are formed because of association. Okay, so these are dispersions of what are called as aggregates, which are formed because of association of molecules. Okay, any examples? What is it? Surfactant molecules, right? So what you do is, you have if you have water, right? All of you know about what is called as a micellization. Yeah, you have heard of term, right? Micellization. So if you take water and I add surfactant molecules, as I said, are typically represented like a head and a tail. Okay, this head is typically hydrophilic, tail is hydrophobic. Now when you put such molecules in water, what will happen is, initially you will have some free molecules, okay, and because of the fact that they are amphiphilic, some of them may go to the interface. I go on adding more and more surfactant, right? More and more free molecules may form here, and of course, and more occupy the interface. When you add enough that the entire interface is completely occupied with surfactant molecules, anything more that you add, okay, it will go and form what are called as molecular aggregates, which are what are called as micelles, right? Typically, they represent micelles like this, right? Okay, all the tail groups are held together at some common location, and you have head groups that face water. Okay, because you have water, right? This is a hydrophilic group, and hydrophilic group is happy being in water, right? So therefore, these aggregates are formed because of association of several number of molecules that come together. Okay, so that could happen if you're working with surfactants. It could happen if you're working with as I said, these blocker polymers and things like that. Okay, so a lot of amphiphilic molecules, when you put it in either water or any other fluid, they form molecular aggregates, which are examples of what are called as association colloids. Okay, so therefore, depending upon the types of the particles of the dispersed phase, you can classify colloids into multi-molecular colloids, macromolecular colloids, and association colloids. Okay, so that's you can think about this as another way of classifying colloids into different types.